the presentation is not visible in full screen mode, let me know. I'm starting the presentation. So firstly, in today's lecture, we'll go through fundamentals of manufacturing processes. Okay, so in previous week, we studied understanding manufacturing processes first part. In this week we'll study in the second part. So this course is offered by Professor D.K. Dwivedi from Department of Mechanical and Industrial Engineering, IIT Roorkee, and I'm your TA Alka Janget from IIT Kanpur. So firstly we'll go through some sample assignment questions which will help you in solving your weekly assignments. After that, we'll go through some lecture notes which will also help you in solving your assignments. So if my presentation is not visible in moving mode to you, then let me know. I'll switch to other modes if it's not visible. Okay, then I'll continue. Okay, so first question is the process that improves. Yeah. It is not visible. If the presentation is not visible in moving mode, then let me know. Okay, so now we'll go through the first question. So first question is the process that improves surface hardness without work hardening effect is. Your options are short peening, burnishing, induction hardening, and contour rolling. So surface hardness improvement can be done by using all these processes, but some of these processes they use the effect of the, for in case of short peening, there are small balls that are used that are after hitting the surface it will induce some work hardening in your material. So in case of short peening, burnishing and contour rolling, all these cases there will be dislocation multiplication in your surface part, so there will be work hardening which will lead to your hardness improvement in your material. Okay, so out of these processes, so the process which improves surface hardness without work hardening effect will be induction hardening, because in case of induction hardening it uses different method. In this case, this method of quickly and selectively hardening the surface of a metal part, it is mainly used for steels. So a copper coil carrying a significant level of alternating current is placed near the part, and the eddy current and hysteresis losses they generate heat at and near the surface, and the quench. Yeah, I think there is some message. Okay. Okay, so for those who joined late, okay, someone else also wants to join. Okay, so for those who have joined late, I'm going through sample assignment questions. So these will be helping you in solving your weekly assignments. So these questions are different from your assignment this week, but these will be helping you. So first question is the process which improves surface hardness without work hardening effect is. The answer will be induction hardening, and in case of induction hardening we use eddy current. Someone else wants to join. Okay, so in this case your eddy current helps in increasing the temperature of the only surface. So there is very thin layer of surface that will be having some heat generated, and this will be after quenching through water, it will lead to some quenching in that part. So through the quenching there will be phase transformation. Now for steel, phase transformation occurs, and because of quenching there will be martensite formation. So martensite has very high hardness. So this leads to hardening in the surface area. So only this method, induction hardening, doesn't use work hardening. If the slides are not visible, let me know. I am on the second question now. So if the slide is not visible, let me know. So the second question is, you can also try to answer the questions in the chat box, so that I can help you in understanding where you are doing anything wrong or how to solve these questions. So if you want, you can answer the questions in the chat box. So second question is, the powder metallurgy process used for manufacturing components made of, and your options are high carbon steel, aluminum alloy, ceramics and magnesium alloy. So your answer will be ceramics. So why the answer will be ceramics? So some alloys also can be made using powder metallurgy, but but in case of ceramics they can't be made using casting. So these other alloys, they can be easily made using casting. So we avoid using powder metallurgy, which is most costly technique, and it also has a restriction of volume as well. So there is only small volume products can be made using powder metallurgy. But in case of ceramics, they have very high melting point. So for ceramics, there is restriction of the manufacturing processes that you can use. So the powder metallurgy is the process which consists of mixing elements or alloy powder, compacting the mixture in the die, and then sintering or heating the resultant shape in a controlled atmosphere. The powder metallurgy is a highly developed method of manufacturing ferrous and non-ferrous materials, and it is chipless working process. So in this case there won't be any generation of chips, such as which occurs in case of machining process. And metallic powders are expensive. When we talk about the other options, these for the formation of these powders, it will be an expensive process, and also these can undergo oxidation due to milling, because surface area will be increasing a lot. Next question is, the process is used to make thread. Now if you are using some, for example, any nut bolt and all, on those you see there is a thread formed on it, or other type of threads that you will be forming. So which process can you use for that? Your options are forging, extrusion, rolling and drawing. Now all these are the formation processes. Now which one will be suitable for the making thread? Yeah, so someone, okay, there is an slides aren't changing. Okay, I'll share the entire screen. Let me know if the slides are visible now. Entire screen share. Okay, let me know if it's visible now, if the slides are visible now. Okay, are these slides dynamic now? Let me know. Okay. Okay, so we were on third question. So which process do you think will be used for making threads? So the answer will be rolling. So in these are the definitions for various processes. Someone else has joined. Okay, I'll admit. Okay, for those who have joined late, we are going through some sample assignment questions. So you can also try to solve these questions. You can type the answer in chat box, so that I can understand how much you are understanding the answers and how much I need to work. So third question is which the process used to make thread. Answer will be from rolling. So these are the definitions for various these processes. So in extrusion, a required shape is created by forcing the billet out from the die. So this die will be having some cross section, which will be desired cross section, so you can make it in form of a sheet or some uh, cuboid shape, some cube shape. So these shapes will be similar throughout the cross section. In case of rolling, it is a process used to reduce the thickness of the die by using rollers. And in forging, so in rolling you can choose rolls in such a way that it will be forming threads on your rod. And in case of forging, the shape is given to the workpiece by application of compressive forces. And in forging, you will be mainly doing hammering. So using hammers, you will be providing some compressive forces. Wire drawing or drawing is a cold plastic deformation process by which the diameter of a rod or a wire is reduced and its length is increased by pulling the workpiece through the calibrated hole of a conical die. So wire drawing is mainly used for making wires or reducing the diameter of the wires. Next question is, correction in size and shape of existing holes can be achieved by. So your options are drilling, milling, boring and shaping. So answer will be boring. So in case of drilling, what you do, you make a new hole using the drill bit. And in case of boring, you'll be widening the existing holes, which can be made using either casting or either using drilling. Okay, so these are the definitions of various processes which might be useful in your assignment questions. So first is drilling process. In this case, a tool creates or refines round holes in a workpiece, and this is usually done through a rotary tool with 2 or 4 helical cutting gauges. Now I think drilling process you all must have seen at some point. Milling process, this is the type of tool that creates designs by removing material from the working piece by rotating a cutting tool. Boring is a process of enlarging a hole that has already been drilled or cast by means of single point cutting tool. Shaping is a machining process whereby a workpiece is held on the machine table, which is then advanced into the path of a reciprocating ring, upon which is mounted a single point cutting tool. Okay, so next question is, increasing strength of steel due to martensitic formation is an example of. Your options are work hardening, transformation hardening, grain refinement and precipitation hardening. So these are various strengthening mechanisms. I'll be discussing these in lecture notes as well. So work hardening is basically in this case you'll be strengthening your material by deformation. So you'll be deforming your material, which will lead to multiplication of dislocations. Now these dislocations, because of they'll be interacting with each other and their movement will get difficult, so this will lead to strengthening of material. And in case of transformation hardening, it is basically phase transformation. So when the formation of martensite occurs from austenite, it is a transformation hardening. Okay, so transformation hardening is hardening due to phase transformation. Third is grain refinement. So in this case your strengthening will be due to reduction in crystallite or grain size of material. Precipitation hardening will be hardening due to formation of precipitates. So for example, your uh, aluminum copper alloy or your stainless steel, these will show precipitation hardening. So and these precipitates, they interact with dislocation, which leads to dislocation multiplication and then again strengthening. So in this case, when we talk about steel and formation of martensitic formation, then it will be transformation hardening. Next question is related to your cost, which now there are three methods that you can use, and which method will be giving you least cost. So one automobile industry needs crankshaft and it has three choices. The manufacturing can be by casting process, forming process and purchase from the vendor A. So you can either directly purchase these units, or you can either use casting or forming process. So the fixed cost and variable cost related to both processes are in the table below. And the vendor A supplies crankshaft for 1500 rupees per unit. Okay, so you have to find out total cost for all these three methods. So in case of casting process, you have fixed cost of 5 lakhs, and in case of variable cost will be per unit. Okay, so it will be varying with the unit, so it is 700 rupees. In case of forming process, it is 12 lakh is the fixed cost and 400 per unit is the variable cost. Now you have to select the best choice if the 1000 units are to be needed. So your options are casting, forming, purchase from vendor A, or all of these. So answer will be casting process. Now how to solve this? So in case of casting, it is a process of melting and shaping material. So in this case, total cost will be addition of fixed cost plus variable cost times the units. Okay, because it is per unit, so you have to multiply units with it. So 700 multiplied by 1000 plus 5 lakhs, so it will be 12 lakhs. In case of forming process, it is working of material to bend or roll material. So in this case, your fixed cost is 12 lakhs and your variable cost is 400. So you multiply it with units, so it will be 16 lakhs. In case of when you directly purchasing, so in this case your total cost is 1500 times 1000, so it will be 15 lakhs. So the least cost will be from the casting, so casting will be the answer. Next question is, refining the grain size of a metal can either decrease the hardness, decrease the strength, increase the strength, or ease of dislocation motion. So which statement will be correct? You have to find out. Okay, so we just few slides back we studied that. Okay, so grain refinement we studied, it is strengthening due to reduction in crystallite size and grain size. So here we are doing the same thing. So we are refining the grain size, so it will be increasing the strength. Now this is the theory behind it. So if you have, I don't think you are able to see the pointer. Okay, now you are able to see the pointer. Now this is one of the grains and this is another grain. Okay, now when a dislocation will be moving, this is one of the dislocation, so its movement will be hindered at this grain boundary. This grain boundary is the areas where atoms are not at the equilibrium distance. Now in these areas your dislocation won't be able to move easily, so it will have to change the slip plane. Now because of this there will be pile up of dislocations at this point, and because of that there can be multiplication as well. Now this will lead to increase in strength of material. For high angle grain boundaries, the dislocation will not traverse across grain boundaries and the dislocation pile up at the grain boundaries. Now there will be a lot of dislocations piled up, and this introduces stress concentration ahead of their slip planes, leading to new dislocation creation in adjacent grains. and a fine grained material is harder and stronger compared to its coarse grained counterparts. So the smaller these grains are, the harder will this material become, and this reduction in grain size also increases toughness. Next question is the factor which affects buoyancy force on the core in casting is or are. So you have to find out which ones are correct. So which will affect this buoyancy force? Either density of molten metal, density of core, volume of core, or all of these. So answer will be all of these. Now the factors which affect this force, these are density of the fluid. Fluid will be your liquid metal that you are pouring. Volume of the fluid that displaced, volume of the body that is submerged in liquid, which is the core, and acceleration due to gravity. These all will be affecting this force, and this force is not affected by the mass of the immersed object. Next question is fluidity of molten metal is dependent on. Your options are surface finish of the mold, specific heat of metal, melting temperature of metal, or thermal expansion coefficient of metal. So your answer will be specific heat of metal. Now fluidity of molten metal is dependent on various factors, and so firstly we need to define what is fluidity. Okay, so fluidity refers to how easily the melted metal flows into the casting, and the specific heat is the energy which is used to raise temperature necessary to melt into liquid form. Okay, so fluidity in the foundry science is defined as the ability of molten metal to flow before it is stopped by solidification. So if a material has high fluidity, then it will be easily formed into complex shapes through solidification. Okay, so fluidity is quantified by measuring the length of a molten metal will flow when it is poured into a small cross section channel. So this is one of the method how to measure fluidity, and the mathematical model for estimating fluidity length was proposed by Flemings, and the model provides the following equation for calculating flow length. So this is the length of flow. So there are various factors, you don't need to remember this formula. This is just for telling why the correct answer is specific heat of metal. Okay, now in this formula one of your Cp is there. So Cp is the specific heat of metal. A will be your mold that you have used, its cross section. Rho is your liquid density. V naught is flow velocity. Critical fraction, solid for flow stoppage, heat of fusion, all these other things, melt superheat, all these also affect your fluidity. So melt superheat meaning how much you are heating your material above melting temperature. So if you'll be heating it more above the melting temperature, then it will be having higher fluidity. Okay, now all these parameters, these will be affecting, and there is not among these parameters there is not thermal expansion of coefficient or melting temperature or surface finish of the mold. Next question is, in sand casting, difference in the solubility of gases in solid and liquid state of metal leads to the formation of, your options are oxide, nitride, porosity, or shrinkage cavity. Now the solubility of gas is always higher in case of liquid state compared to solid. Now when the liquid suddenly solidifies, then these gas get entrapped inside this solid. So this entrapment causes formation of pores. So gas pores will be there. So porosity will be the correct answer. So the porosity is among the most common casting defects which occurs when a pocket forms due to air or gas trapped in the metal during solidification, which is gas porosity. And the porosity is also caused by the metal shrinking, leaving voids in the center of the metal, which is shrink porosity. So there are two types of porosity. And the shrinkage is a cavity or depression in casting which occurs as the material cools to become solid. And the shrinkage porosity has angular edges rather than round edges associated with gas porosity. And the shrinkage should be factored into all casting processes. So there are some tolerances that are taken for the shrinkage. Now we'll go through some lecture notes. So you let me know if you want me to go through some questions that you are not able to. Okay, there is someone has written. Okay, we'll go through lecture notes. So first chapter is selection of manufacturing processes. So firstly, criteria. So the product based. So there can be different criterias for selection of manufacturing processes. Okay, so you can choose your manufacturing process either based on your product that you require, or on requirement of what are the properties that are required, or what are the cost of the particular manufacturing process. Okay, so first is shape of final product. So what shape you require, or what is the size of the product that you require, or raw material that you require, which can be hard or brittle, or what's its melting point. These also will decide what manufacturing process that you choose. Design requirement. So it is features, holes, slots, notches. If you require these, then which manufacturing process you will choose, that will also come into play. Next is dimensional and surface properties. So in this case, what will be the final size, final thickness, or shape complexity? So if the shape is very complex, then you, for example, you can use some forming processes such as extrusion. And if there is some tolerance or surface finish requirement, then you can basically use sand casting. And what are the properties needed? If you, for example, if you require high isotropic properties, so if you want your properties to be very uniform throughout the cross section, then you can't use sand casting, because it will lead to formation of some anisotropic properties. Operational cost. So it is based on design and tooling cost. So for example, if you are using machining, then you require some tooling cost for lathe machine or CNC or different machines. Lead time will be when you start your process and you complete your process. In between that, your time will be lead time. Okay, now your choice of the manufacturing process will depend on lead time as well. Minimizing scrap. So in case of powder metallurgy and casting, there is less amount of scrap generated compared to machining. And volume of production. So for example, in case of additive manufacturing, you are restricted in terms of, in case of additive manufacturing, the volume has restriction. So there is only smaller amount of volume that you can produce in one go. Availability of system needed. Next is, I showed this graph in previous class as well. So in this case, we saw that with the production volume, how much, yeah, so manufacturing processes. Someone else has joined. First let me admit. Okay, for those who have joined late, I am going through lecture notes now. Previously I went through sample assignment questions. So firstly, now I am going through lecture notes. Okay, now this graph I showed earlier as well. Now this depends on this tells with basis on melting temperature and based on production volume that you can use. So with deformation processes you can produce higher volume production volume compared to material removal processes. Next up, according to batch size. So if you require only few units of particular product, then you can choose flexible manufacturing processes such as machining, which can produce variety of geometric features. And if your batch size is very large, so you require very large number of units, then it allows use of primary forming and deforming processes so as to offset the relatively high cost of machine tools. So you'll be requiring a lot of amount of money to buy these machine tools, so that can be covered by the this large batch size that you are producing. Okay, now these are the numbers of units, and based on those how you can select these processes. So if you require only 500 units, okay, let's say 500 units, then machining process you should choose. Or if you require only up to from 7.5 onwards, then you will be using primary forming processes, and more than 1000, then you will be using deforming processes. Next, according to type of work material. Okay, so this can be metals, and most of the metals. So in metals, they have relatively high melting temperature, and they can be processed in solid form using machining and deforming processes. And for the metals which are difficult to machine, which have poor machinability, then additive manufacturing processes are commonly preferred. And for example, for polymers and epoxy based composites, if they have lower melting point, then these can be processed in liquid state. And some secondary processes like machining is needed to obtain desired dimensional accuracy and surface quality. And sometimes additive manufacturing processes are preferred for polymer matrix composites with fibers and fillers due to their brittle behavior. In case of ceramics, these are usually brittle, so it is very difficult to process in solid form using conventional machining processes. So special processes like powder metallurgy techniques are used, and additive manufacturing processes are used to give final shape and surface for modifying surface quality. Now these are the various numbers that are there for choosing based on roughness, what will be the final roughness of the product, and what will be the tolerances in your product. So it is given for all the processes such as sand casting, plastic molding or machining, and non-traditional processes as well. Next is applications of manufacturing processes. Now in case of casting has a lot of applications. Firstly, in automotive sector, so in this case, piston, cylinders, alloy wheels, engine blocks, carburetors, and your transmission housing, crankcase, brakes, these all using some alloys such as aluminum, magnesium, zinc and cast iron, and rail wheels, all these are made using casting. And in case of propellers of copper based alloys for ships, and these casing, covering and impellers for centrifugal pumps. Impellers are the rotating blades, and propellers are also blades which are not covered by encasing. So these all are all made by casting. Turbine blades and discs for high temperature applications, large diameter shafts for hydropower plants, all these are made using castings. The gear blanks are the part of gear that is made before you pass your gear through some for making the tooth on the gear, and this is used for cement industry. These are also made using casting. In case of municipality, your pipes, main hall cover, bench, chair parts using cast iron, bell casting, all these are used. All these use casting as well. Raw materials such as blooms, billets and strips, these are also made using casting. Jewelry, ornaments of gold and silver. Next up, specific casting processes. So in case of sand mold casting, so in this case your mold will be made using sand. So in this case your piston, cylinder, engine block, air compressor frame, carburetor, all these are made using sand molding. Die casting, in this case your mold will be made of using dies. Dies can be made of some metals. So in this case your cooling of the material will be very fast. So alloy wheels, complex shape products, these are made using die casting. Shell mold casting, in this case your mold will be made using some shells, which can be, someone else has joined. Okay, so in case of shell mold casting, your shells will be providing a precision to the gears, valve bodies, bushing and camshafts. Investment casting, uh, about these castings we'll be studying in detail in next chapters, but here we are just going through what will be the applications, because you'll be asked questions based on these as well in this chapter. So some statues, medals, jewelries, blades for turbines, dental fixtures, all these can be made using investment casting. Centrifugal casting, this is used for making pipes, tunes, bushing, rings and solid parts with high density. So in this case, centrifugal casting, the presence of pores and various defects will be very less. Next is forming processes. Now for these applications, in case of automotive, you have connecting rods, crankshafts, body of automotive, pressure vessels. So the things that you have already prepared using casting, you require some forming processes as well after that. And aircraft panels, fuselage is the near wings. You have the body part of the your aircraft is fuselage, and wings, these all are all made using forming processes. Tools such as handle tools, spanners, wrenches, hammers. Raw materials such as sheets, plates, wires. So wires, rods, these are made using drawing. Plate, sheets, they are made using rolling. Tubes, girders, beams, rivets, springs, these are also made using these forming processes. Hooks for materials handling, these all are made using forming. Now application specific forming processes. Now using rolling, you'll be making standard plates, sheets, I-beam sections, thread and gear rolling, roll piercing for tubes. In case of forging, you can make crankshaft, connecting rod, gears, blooms and slabs, coining. In case of extrusion, it will be having uniform cross section rod, bars and tubes. In case of drawing, you can make wires, bars and tubes. Next is machining. So machining of almost all components made by casting, forming and welding is needed to get desired size and shape, finish and tolerances. Pipes, pistons, cylinders, nut bolts, crankshaft, bearing, shafts, casing, gears and engine block, carburetor, etc. all these are made using machining. So machining is a secondary process. So you will be providing some precision and all those tolerances. So to reduce roughness as well, you will be using machining. Now specific machining processes. So first is turning. So you can make cylindrical shapes, holes, contour profiles, taper, nulls. In case of milling, you can make flat surfaces, slots, keyways, contours, gears. And in shaping and planning, you can make flat surfaces, slots and grooves. In case of drilling, you will be making holes, contour bore and sinks, centering and reaming. In case of case boring, you will be making enlarging and correcting existing holes. In case of grinding, you can make using crankshaft, camshaft and flat surfaces. Next is welding. So in this case, in case of automotive parts, you can make car body and panels using because some of the parts need to be welded. It can be made in one go. In case of petrochemical, your gas cylinders, pipelines, LPG carriers and steel structures, these are made using petrochemical. Railway, so rails, carriage, wagons, these are made using welding. In case of construction, joining of reinforcing bars, structures and bridges, this is made using welding. Now there are various applications of weldings. In case of these are the specific. For example, in case of automobile, you can use resistance welding, and rail joints and railways, you can use thermite welding. So thermite welding is also used in case of railway tracks for joining those, and for for removing any damages that are there on railway tracks. In case of aerospace and nuclear reactors, you use TIG is tungsten inert gas welding, and ship work is submerged arc welding, and pressure vessel are the vessels that will be holding some gases at high pressure, or that will be holding your vacuum at someone else has joined. So pressure vessel can hold vacuum as well, vacuum or gases at high pressure. So pressure other than your room pressure, your atmospheric pressure, then it will be called pressure vessel. So these will be welded using SAW, which is submerged arc welding, or gas metal arc welding. And joining of metals, so it can be for stainless steel, aluminum and magnesium. These are sensitive to atmospheric gases, so metal inert gas welding, this will be used. For the specific welding, in case of transport tankers for transporting oil, water, milk, welding tubes and pipes, chains, LPG cylinders, steel furniture, gates, doors and door frames, body, and white goods such as refrigerators, washing machine, microwave ovens, all these require the application of welding. Now these are the pressure vessels which will be requiring welding. Bridges, in case of bridges, with advancement of welding technology, however, now welded bridges structures are also common, and welding found its place in shipbuilding around 1920, and presently all welded ships are widely used. And there is underwater welding is also possible, in which case your shielded metal arc welding is used. So your metal that is used as electrode, which will be covered in, which will be made waterproof by some cover, it will be shielded. Building structures, now arc welding is extensively used for fabricating steel structures such as trusses, tower trusses, meaning some these type of the image that is shown, which is made of various of these beams. Okay, some structures that will be like this, skeleton structures. Towers and in construction industry and in transport industry. So aircraft and spacecraft, they use spot and tungsten inert gas welding, which is widely used for fabrication of aircraft structure and joining of skin sheet of body. In case of railways, for fabrication of coaches and wagons, or laying of wheel, joining of rails by mobile flashbird welding machines, and repair of cracked damaged tracks by thermite welding. You will be studying what is thermite welding and all these weldings in next few chapters, but you should have like what will be their uses for now. So this is the I think you are able to see pointer. Yeah, now this is the one of the joints that is made using welding. Automotive industry, the fabrication of automobile components like chassis. Chassis will be the skeleton of your skeleton and basis of your car body, and then the body, that will be, you'll be using metal sheets, then those connection of all those parts will be using welding, and the structure, fuel tanks and joining of door hinges require welding. In case of electrical industry, most of the engineering systems used in electrical industry are fabricated using welding. Generation, in this case penstocks, water control gates, condensers, turbine plates and cooling fins. In case of electrical distribution, so electrical transmission towers and distribution system equipment, transformer, these are made using welding. Utilization of electrical energy, so electrical motors, stators, these will also use welding. Nuclear industry, so welding is used for fabrication of spheres for nuclear reactor. Pipeline blends, joining two pipes carrying heavy water. Defense industry, for joining of many components of tank bodies, fabrication, joining of turret mounting. This is the part in tanks when you see the part that moves for firing any weapons. Okay, that part will be this mounting to main body. This will be connected using welding. Oil and natural gas. Now in this case, welding is used for join pipes while laying of the crude oil and gas pipelines. Construction of tankers for their storage and transportation, offshore structures, dockyards, loading and unloading cranes. Micro joining, and these will be thin wire to wire, foil to foil and foil to wire for producing junctions of thermocouples and strain gauges. Next is effect of manufacturing processes on mechanical properties. Now the scope, so how you choose your manufacturing process will ultimately affect the properties that will be in your final product. Okay, so manufacturing process affect the microstructure of metal during processing, and the microstructure in turn affects mechanical properties such as hardness, strength, ductility, toughness, fatigue and creep resistance. Therefore, such variation in mechanical properties must be kept in the mind for ensuring that end product has requisite properties for service desired. For example, if you are using grain refinement, so if you are cooling your casting very fast, then the grains will be fined. So in that case, you will be having proper toughness of material, and also in case of casting, you have lower hardness and strength. Now we'll be going through the various processes. So first is casting. In case of cast structure, you will be having low hardness. Why low hardness? Because the structure, microstructure won't be very sound. and you will be having a lot of defects in it. Okay, so it will be having low hardness, low strength, low toughness and low ductility. So for ductility also, your rod type of materials where you provide some deformation to it, then it will be having better properties. Scope of internal defects, so there possibility of presence of some porosity, heterogeneity in terms of composition and property. So as I told earlier, if you are casting your material at a higher cooling rates, then there will be heterogeneity in the your microstructure. So there will be formation of columnar type of structures or dendritic type of structures which will be heterogeneous. Now there are various types of structures that are possible in casting, such as planar, cellular, dendritic and equiexed, based on your the size of mold and the thermal conductivity of the mold, and what will be the the cooling rate. So all these will determine what will be the final microstructure of your material, and based on that your mechanical properties will be related to that. So if you have aqueous material, then it will be having better properties compared to dendritic and cellular type of structures. In case of welding, you can have three types of welding. So one can be liquid state, where your joining part will go in liquid state. So in this case, your cast weld metal and heat affected zone will be there. So these will be deciding what will be the properties of final product. In case of solid state, you'll have affect the properties as per the strengthening mechanism, weld nugget and heat affected zone. In case of liquid solid state, it does not affect the base metal properties, but joint strength is poor. So in case of braced and soldered joints, you will be having lower strength in the joint. So these joints are not used when you will be using this final product in an application where you require very high strength or tensile strength. Next is machining. So in case of mechanical machining, you will be having shearing type of forces. So it will lead to compressive residual stresses at the surface, which will lead to improved fatigue and tensile properties. In case of thermal, you will be having melting and ablation, and they will be having a recast layer. So there will be some layer which will melt and again get solidified. So they will be having heat affected zone, which may cause abrupt change in properties as per metal system. So if your metal system, for example, if it is steel and if it has very high hardenability, then it might form martensite. So it will be having very high hardness at the surface. Next is chemical. So in this case, electrolysis. Someone else has joined. Okay. Okay, so in case of machining, you can have chemical, in this case electrolysis, so there will be no residual stress. So if you are removing only small layer from the top of your material using chemical electrolysis, then there won't be any residual stresses formed. Okay, so lower fatigue will be there, lower fatigue properties and tensile properties will be there with respect to sheared surfaces, because there you were getting better properties due to compressive residual stresses. Next you have forming processes. So in case of cold forming, you will be having increased hardness and strength. So cold forming will be occurring at room temperature. Okay, so in this case you will be also having reduced ductility, and there will be formation of notches. You will be having reduced internal defects, and you'll be having better finishing and closer tolerance, and you'll be having increased strength to weight ratio compared to other processes. In case of hot forming, you'll be having a temperature higher than the room temperature. Okay, so higher than recrystallization temperature. So your controlled refined microstructure. So because of recrystallization, so you will be having a refined microstructure. So grains will get refined. And then it will be having improved mechanical properties compared to cold forming, and it will be having less anisotropic properties. So there will be such a cellular type of structure in cold forming, so that won't be in case of hot forming because you are getting dynamic recrystallization, and there is also no residual stress. Next is break-even analysis in case of manufacturing processes. So firstly, why we need break-even analysis in manufacturing? So we need to select a manufacturing process to make product as per specification of required properties or quality and at the lowest possible cost. Okay, so since different processes offer different capabilities and cost per unit, therefore break-even analysis is needed so as to select suitable process. Now there are various types of costs. So first is fixed cost. So in this case, fixed cost, for example, if you are doing casting, then you need to buy a furnace. So that will be a type of fixed cost for you. You need to purchase furnace only once. So that's why it will be fixed cost. Variable cost. So if you're, for example, if you're making some product from aluminum, so if you need to buy, if you need to make 1000 units, then you need to buy material at various times. Okay, so that will be your variable cost, the cost of material. Okay, so fixed cost will be initial investment on equipment and tools. It doesn't vary with volume of production. Variable cost will be, it varies with volume of production and includes materials, energy, labor, administrative overheads. Okay, so for example, if your aluminum scrap will be your variable cost, the electricity that you are using for your furnace, that will be variable cost. Labor, administrative overheads, if you are using some person who will be doing this work for you, so he will charge labor per day, that will be your variable cost. Okay, so this variable cost will change with the number of units. Total cost will be fixed cost, which will be added only one time, variable cost multiplied by number of units. Now the total cost per units decreases with increase in quantity as fixed cost remains same. So break-even analysis. Now this is the graph. So for example, you see the red line. This red line is your fixed cost. Okay, so this much amount for buying your tube furnace or any other furnace. Okay, now you have purchased this furnace, this cost will remain same. This green line is the variable cost which is changing. So the aluminium amount will keep on increasing with the amount of products you require. Okay, so now combined these will be your darker red line. This will be your total cost. Now you can either use casting or you can directly buy your units as well. Okay, so you will be buying 0 units, then you will be having your 0 amount. Okay, in this case for 0 you will be having some amount of fixed cost. Okay, you will buy your tube furnace, that will also cost you without even making any product. So in case of purchasing, it will start from 0. This graph will start from 0. Okay, so it will be the cost of one product times the number of products. Okay, so this will be a straight line. Now you will be comparing this with the machining. If you are comparing it with machining with outsource, meaning purchasing, then there are two lines. So where these are crossing, so below this, purchasing directly is cheaper, and after that your machining becomes cheaper. Now break even for the three processes. So you are either buying, you are either using milling, you are either using CNC. Now there are crossover points you will be finding. Now based on those, there are three ranges. So in this range, your purchasing will be cheaper. In this range, your milling will be cheaper, and after that CNC becomes cheaper. Now cost of 1000 units, and you have chosen three processes A, B, C. Now A is directly buying, and in here your one unit is costing you 200 rupees. So 2 lakh will be the entire cost. For B, you have fixed cost 80,000, and your 75 is per unit cost, and 1000 is number of units. Okay, so 1,55,000 will be the entire cost. In case of C, you will be having 2 lakhs as the fixed cost, and 15 is the for per unit cost, your variable cost. So this will be 2,15,000. So which one will be cheaper, you can figure out by using these equations. Now next, you can draw these lines and find out at various ranges. So previously you saw for 1000. At 1000 you can see B is the cheapest method, and at 2000 we can see B and C both are equal. So 2,30,000 is both are equal, and A is the highest cost. Now at 3000 units, you can see C method will be the cheapest. So C will be having 2,45,000, while others will be having 3 lakh and 6 lakh. So those are more expensive. Now break even analysis. Now when does lathe become cheaper than the outsourcing? Now you can find two equations and equate them and find out where those two will be equal. Okay, now the equation for this, for B and A, you can equate. Okay, and you will be getting x equal to 640. So after 640 you will be having before 640 directly buying is cheaper, and after that you are having this B as cheaper. And for finding out this point, you'll have to equate two other equations. Okay, so when does machining center become cheaper than lathe? Okay, so 80,000 plus 75 times x will be equals to 2 lakh plus 2 lakh is fixed cost for other your other method, plus 15 times x. So from this you will be getting value of x as 2000. Okay, now from 640 to 2000, in between that your lathe will be cheaper, and below that 640 you'll outsourcing or directly buying will be cheaper, and after 2000 your machining center will be cheapest. Next is final chapter is casting, introduction and suitability. Now casting is a manufacturing process in which a liquid material is usually poured into a mold which contains a hollow cavity of the desired shape and then allowed to solidify. Now the suitability of casting, so it can be used to create complex internal and external part geometries, and some casting processes can produce parts to neat shape which require no further manufacturing operations. and can produce very large parts as well. So cast parts can weigh over 1,100 tons, which have been made, and these can be used, casting can be used with any metal, which can be heated to its liquid phase. And some types of casting are suited to mass production as well. Now these are various parts. So most of these are part of some automobile. So these all parts are made using casting. Now these all have good surface finish as well. Now some questions were based on hardening and strengthening mechanisms, so I'll go through those briefly besides the lecture notes. Okay, so these are not part of your lecture notes, but I'm going through these because you had 2 questions based on these. So firstly, the ability of metal to plastically deform depends on ability of dislocations to move. So your material, if you're applying some stress on your material, then it will be having movement of dislocations. Okay, now this restriction or hindering dislocation motion makes a material harder and stronger. So as the number of dislocation will increase, your material will become stronger. Okay, so these are some mechanisms to strengthen metals. First is grain refining, then solid solution strengthening, strain hardening, precipitation strengthening. These all will be studying, these 2 won't be studying here. So next is martensitic strengthening, which is transformation strengthening. Okay, so in this case, your steel, when you'll be quenching it, then there will be formation of martensite, which has very high hardness. Next is composite strengthening. So in case of materials, when you'll be adding some fibers or some other reinforcements, then it becomes composite. Okay, now this will also provide some strength to material. Now firstly we'll be going through grain refining. Okay, so in this case, a fine grained material that has small grains is harder and stronger than a coarse grained. So due to a greater total grain boundary area to restrict dislocation motion. Okay, so this is the Hall-Page equation, which is sigma naught equals to sigma I plus ky upon under root d. Okay, so sigma naught is yield strength of material. Sigma I is frictional stress which opposes the motion of dislocation. Ky is the extent to which dislocations are piled up. D is the average grain size. So the critical grain size, which is typically around 10 nanometer, and the yield strength would either remain constant or decrease with decreasing grain size. So this phenomena is known as inverse Hall-Page relation. So if you keep on decreasing the grain size below 10 nanometer, then you won't be seeing this strengthening. So the equation is not valid for very large grains and very extremely fine grains. So in case of grain refining, your grain boundary acts as a barrier to the dislocation motion, and 2 grains are of different orientations, and a dislocation passing into grain B will have to change its orientation. So the atomic disorder within the grain boundary region will result in discontinuity of slip planes. So from this part also you can understand, this part here it is grain boundary. So here the atoms are not at the equilibrium distance. That's why this is the discontinuity of slip planes. And here you can see that there is graph between yield strength and grain size. So as the grain size will keep on decreasing at this side, your yield strength will keep on increasing. This is for the copper zinc alloy. Yeah, next is, do you have any question? So in this case, as I told earlier, this is the grain boundary part and these are two grains. Okay, so as the dislocation will move in this part and it will encounter these grain boundaries, then there will be formation of pile up of dislocations at this side. Okay, now this is the, in case of high angle grain boundaries, dislocation will not transverse across grain boundaries and the dislocation pile up at the grain boundaries. This introduces stress concentration ahead of their slip planes and it leads to a new dislocation creation in adjacent grains. And a fine grained material is always harder and stronger compared to its coarse grained counterpart. And this reduction in grain size increases the toughness also for many materials. Next is solid solution strengthening. So here you can see that there is the impurity or some solute atoms that will be present, this yellow and this blue atoms. These will apply some strain to the lattice. So this strain will provide some strengthening to this material. So pure metals are almost always softer than their alloys, and adding another element that goes into interstitial or substitutional positions in a solution always increases strength. So the purity atoms, they cause lattice strain which can anchor dislocation. So if there, for suppose there is a dislocation movement is there, then this dislocation will be hindered because of these impurity atoms, because there will be interaction between the strain due to this atom and strain due to this dislocation. So alloys are always stronger than pure metals, and here also you can see as the nickel content increases in copper, the tensile strength keeps on increasing and ductility keeps on reducing. Next, alloying with impurity atoms that go into the substitutional and interstitial locations improves strength and hardness, and high impurity metals are usually softer and weaker than the alloys with the same base metal. And the alloys are stronger than pure metals because the impurity metals alloys are stronger than pure metals because the impurity atoms impose lattice strains on surrounding host atoms. So as you can see, these white atoms are host atoms, okay, from the matrix base metal, and the lattice strain field interactions between dislocations and impurity atoms inhibit dislocation motion. So on upper part you can see the atom is smaller in size compared to host atom. So the impurity exerts tensile strain on the surrounding crystal. So there is small impurity, and if this impurity is large, then the impurity will exert compressive type of strain on the surrounding crystal. Next is strain hardening. This is the enhancement of strength with increased plastic deformation, and strain hardening is the phenomena whereby a ductile metal becomes harder and stronger as it is plastically deformed, and it is also called work hardening or cold working because the temperature at which deformation takes place is lower than the melting temperature, and the effects of strain hardening may be removed by annealing heat treatment, which is slow heating and slow cooling of material, and the strength increases but ductility is sacrificed in case of strain hardening. Next is precipitation or edge hardening. So in this technique it is used to increase the yield strength of malleable materials like aluminum, copper alloys, stainless steels, etc., and based on changes in solid solubility with temperature to produce fine particles of an impurity phase which blocks the movement of dislocations in a crystal's lattice. Alloys must be kept at elevated temperatures for hours to allow precipitation to take place, and this time delay is called aging. Now here you can see that this is the aluminum matrix and there is solute copper atoms. Now these atoms will come together when they are heated, when they are provided the precipitation heat treatment. These will come together and form theta double prime phase and subsequently theta phase. Now these are the precipitates that have formed. Now there will be movement of dislocation, then that will be hindered because of these precipitates, and this is the heating cycle that is used for precipitation hardening. So firstly you have to provide solution heat treatment, and then after quenching you have to provide precipitation heat treatment. Now I'll be going through question answers once again. Okay, for those who joined late, you can go through, you can try to answer the questions. Okay, so first question is the process that improves surface hardness without work hardening effect is. Your options are short peening, burnishing, induction hardening and contour rolling. Okay, so try to answer. If you don't understand anything from today's lecture, you can ask queries as well. If you have any question, let me know. Okay, so we'll be going through questions if you don't have any queries. So first question is the process that improves, yeah, I think someone has induction hardening, yeah. So first answer will be induction hardening. So other than induction hardening, all these processes they use the effect of work hardening. Work hardening meaning there will be some deformation in the surface region, so which will lead to dislocation multiplication. In case of induction hardening, you will be using induction to increase heating in the surface area. So in your surface there will be heating, and when you will be quenching there will be formation of martensite. So formation of martensite won't be using work hardening effect. Okay. In case of induction hardening, it is method of quickly and selectively hardening the surface of metal part, and a copper coil carrying a significant level of alternating current is placed near which does not touch the part. An eddy current and hysteresis losses generate heat at the near the surface. And the quench usually, which is water based with an addition such as polymer, so we can use resin as well to cool your material. It is directed at the part or it is submerged, and this transforms the structure to martensite, which is much harder than the prior structure. Next question is the powder metallurgy process used for manufacturing component made of. Your options are high carbon steel, aluminum alloy, ceramics, magnesium alloy. Try to answer. We have gone through entire lecture as well. You should try to answer like how much you have understood. Okay, so answer will be ceramics. So other than ceramics, these can be easily made using melting. So if you go for example, if you go for powder metallurgy for these other options, then it will add to cost and it won't be providing you desired shape and desired size as well, because in case of powder metallurgy you have restriction for the volume as well, volume of the product. So ceramics are the correct answer for this. In case of the powder metallurgy, it is a process which consists of mixing elemental or alloy powder. So your powder can be a single element as well. For example, if you are making tungsten, if you are using tungsten powder and you are making it in form of element, and then you're trying to make it in form of product or alloy powder, it can be alloy as well, and then you compact this using both pressure and heat, this mixture in a die, and then sintering. So sintering will be, you will be providing heating or heating the resultant shape in a controlled atmosphere, so there is no oxidation. Next is powder metallurgy is highly developed method of manufacturing ferrous and non-ferrous materials, and it is a chipless working process. So there won't be any chips formation. So there will be very less wastage of material. And metallic powders are expensive and can undergo oxidation. Next is the process is used for making thread. Your options are forging, extrusion, rolling or drawing. Try to answer. Try to answer in chat box. Okay, so answer will be rolling. So in lecture notes as well, when we studied applications of rolling, there was thread. So in process of extrusion, we make a required shape is created by forcing the billet out from the die. So in this case you will be having a cross section which will be uniform throughout. So you can't make thread using extrusion. In case of rolling, it is a process used to reduce the thickness of the die by using rollers. Okay, so rollers can be having a shape as well, so you can make thread using rolling. In case of forging, it is basically hammering. Okay, so in this, using hammers, you will be giving certain shape to a workpiece by the application of compressive forces. Wire drawing is a cold plastic deformation process by which the diameter of a rod or a wire is reduced and its length is increased by pulling the workpiece through a calibrated hole of a conical die. So your die will be in conical shape, so at the smaller end you'll be passing your wire. Okay, so your wire will keep on decreasing in diameter subsequently, because you can't reduce it in one go, otherwise your wire will break. Okay, so you have to do it in multiple passes. Next is correction in size and shape of existing hole can be achieved by. Your options are drilling, milling, boring and shaping. So which one will be the answer? Okay, so answer will be boring. So drilling is basically making a hole and boring is enlarging the hole that is already been drilled. Okay, so in case of drilling, your tool creates and refines round holes in a workpiece, and it is usually done through a rotary tool with 2 or 4 helical cutting gauges. These cutting gauges are required for the so that your chips can come out of the specimen. A milling process, in this case the type of tool creates designs by removing material from the working piece by rotating a cutting tool. Boring is the process of enlarging a hole that has already been drilled by means of a single point cutting tool or of a boring head containing several such tools. Okay. In case of shaping, it is a machining process whereby a workpiece is held on the machine table, which is then advanced into the path of a reciprocating ram upon which is mounted a single point cutting tool. So increasing strength of steel due to martensitic formation is an example of work hardening, transformation hardening, grain refinement or precipitation hardening. So what should be the answer? You try to answer. We have studied this multiple times in lecture notes as well. Increase in strength of steel. So as soon as you study strength of steel and martensitic transformation, then you should know that it is related to transformation hardening, because your phase is transforming from austenite to martensite. I should have put iron carbon diagram, phase diagram as well here for better understanding. Okay, so work hardening is the strengthening due to deformation and multiplication of dislocations. Okay, so work hardening is your deformation process. Transformation hardening is hardening due to phase transformation. Grain refinement is strengthening due to reduction in crystallite or grain size. Precipitation hardening is hardening due to formation of precipitates and their interaction with dislocations. Next is, this is related to break-even analysis. So we have studied how to tell which process is providing you with the cheapest, with the least cost. So one automobile industry needs crankshaft and it has three choices: manufacturing by casting process, forming process or purchase from vendor A. Okay, so the fixed cost and variable cost related to both processes are in the table below, and the vendor A supplies crankshaft for 1500 rupees per unit. Okay, so in case of casting, you have fixed cost as 5 lakhs, variable cost is 700 per unit. In case of forming process, you have 12 lakh as fixed cost and variable cost is 400 per unit. So you have to select the choice if you have to make 1000 units, and your options are casting process, forming process, purchase from vendor A, or all of these. And the answer will be casting, and you can calculate total cost for all these based on the formula which was told earlier. So you have to add fixed cost plus variable cost multiplied by number of units. So if, for example, if it would have been 2000, then you have to multiply here by 2000, and the answer would have been, it could have been different. Okay, so in this case, for the casting you will be getting 12 lakhs, for forming you are getting 16 lakhs, and for vendor you are getting 15 lakhs. So the cheapest option is casting. Next question is refining the grain size of a metal, and your options are decreases the hardness, decreases the strength, increases the strength, or eases the dislocation motion. So the answer you should try to answer. Okay, so answer will be increases the strength. Okay, so as I told earlier, your movement of dislocation becomes difficult as you decrease the grain size. So as the grain size will keep on reducing, your dislocation movement will become much difficult which will lead to improvement in strength and also improvement in, not improvement, but there is no deterioration in toughness. Okay, so for high angle grain boundaries, the dislocation will not traverse across grain boundaries, and the dislocation pile up at the grain boundaries, and a fine grain material is harder and stronger compared to its coarse grain counterparts, and the reduction of grain size increases the toughness also for many materials. Next is the factor which affects buoyancy force on the core in casting is or are. So your options are density of molten metal, density of core, or volume of core, or all of these. Answer will be all of these. Okay, now these are the factors which will affect the buoyancy. Okay, so the density of the fluid, volume of the fluid that is displaced, and volume of the body submerged, meaning the core, acceleration due to gravity, these all the factors that will be affecting, and the factor that won't be affecting is the mass of the core. Next question is fluidity of molten metal is dependent on. Your options are surface finish of the mold, specific heat of metal, melting temperature of metal, and thermal expansion coefficient of metal. Answer will be specific heat of metal. Okay, now this is the formula that is used here. So firstly, fluidity definition. So it refers to how easily a molten metal flows into the casting, and specific heat is the energy used to raise the temperature necessary to melt into liquid form. Okay, so fluidity is the, in case of foundry science, it is defined as the ability of molten metal to flow before it stops by the solidification. So fluidity is quantified by measuring the length a molten metal will flow when it is poured into a small cross section channel, and a mathematical model for estimating fluidity length was proposed by Flemings, and the model provides the following equation for calculating the flow length. Okay, so this length is dependent on this formula. A is your mold cross section area, rho is your liquid density, V naught is the flow velocity, FSCR is the critical fraction solid for flow stoppage, DH is heat of fusion, Cp is specific heat of metal, and dt is the melt superheat. Melt superheat meaning how much you are heating your material above the melting temperature. So delta T, dt delta T will be the, so if you are heating your material to higher extent to melting temperature, then it will be more having less viscosity and high fluidity. H is the heat transfer coefficient between mold and metal. S is the circumference of the mold channel. T is the temperature of the liquid. T naught is the room temperature, and K is the constant depending on H, the heat transfer coefficient, and hence resistance to heat flow. Next question is, in sand casting, difference in the solubility of gases in solid and liquid state of metal leads to the formation of. Your options are oxide, nitride, porosity, shrinkage, cavity. So what should be the answer? You can type it in chat box. Options are oxide, nitride, porosity and shrinkage cavity. So answer will be porosity. So there is always a difference in solubility of gases and solid and liquid. So when your material will start solidifying, then some gases will get entrapped because there is less solubility in solid. Okay, so porosity is among the most common casting defects which occurs when a pocket forms due to the air or gas trapped in the metal during solidification, which is gas porosity. And this porosity is also caused by the metal shrinking, leaving voids in the center of the metal, and this is shrink porosity. So there are two types of porosity. One can be gas porosity because of entrapment, and one can be due to shrink porosity because of the density difference in solid and liquid. Shrinkage is a cavity or depression in a casting that occurs as the material cools to become solid, and shrinkage porosity has angular edges rather than round edges associated with gas porosity, and shrinkage should be factored into all casting processes. So there are always tolerances given for shrinkage. So there is a higher size of the casting mold is made so that if there is any shrinkage, so that can be taken into account. Now I'll be going through lecture notes once again for those who joined late. Okay, so firstly, how we select the manufacturing processes. So this can be based on either products or it can be based on the cost. So what will be the shape of your final product, the raw material which is hard or brittle, or what will be the melting point of your material that you are using. Design requirements, which can be features, holes, slots, notches that can be present, and dimension and surface properties such as size, thickness and shape complexity, tolerance and finish. And for example, in case of machining, you get very good finish, surface finish compared to sand casting. So if you require some product which requires very good fatigue resistance, so in case of fatigue resistance you require very good surface finish. So you require a manufacturing process which doesn't leave any keyholes or some porosity on the surface. Properties needed. So based on property that you require, you choose your manufacturing process. Design and tooling cost, lead time. So throughout the process, what will be the time required? Minimizing scrap. So scrap will be higher in case of machining, and it will be less in case of powder metallurgy. Volume of production, availability of system needed, these all will decide what manufacturing process you select. Next is application range of manufacturing process. So I told about this graph earlier as well. Next is according to batch size. So it depends on, if you have smaller batch size, then you choose a flexible manufacturing process such as machining, which can produce variety of geometrical features. Larger batch size allows use of primary forming and deforming processes so that to offset the relatively high cost of machine tools and tooling. So if you require number of units, based on that they have provided you with optimum options. So if you require units higher than from 75 onwards, then you choose primary forming processes, and if more than 1000, then deforming processes, and up to 500, then it is suitable for machining processes. According to type of work material. So if your material is metals and alloys, then these metals have relatively high melting temperatures, so they can be processed in solid form using machining and deforming processes. And if they have lower melting temperature, then you can easily cast it using casting. Okay, so for difficult to machine metals and alloys, in that case, if it has poor machinability, then you go for AMP, which is additive manufacturing processes. Polymers and epoxy based composites, so it is lower melting point, it can be processed in liquid state. Some secondary processes like machining is needed to obtain desired dimensional accuracy and surface quality. Sometimes AMPs are preferred for PMCs. PMC is polymer matrix composites with fibers and fillers due to their brittle behavior. In case of ceramics, if they are usually brittle, so these are difficult to process in solid form using conventional machining processes. So there are special processes like powder metallurgy techniques are used, and AMPs are used to give final shape and surface quality. Now these are some of the ranges for various processes in terms of roughness and tolerances. So you can select based on that as well. Now these are the applications which I'll skip because these are pretty straightforward. You can just once go through these and try to remember. So if you'll remember, for example, for rolling, which applications are there, so it will be easier to answer in your exam. Okay, so for example, if you are asked connecting rod, which of these forming processes are used, you can be asked in that manner. So you can't answer extrusion, drawing or rolling. So you should know that it is made using forging, because forging provides with good final properties. So there will be compressive stresses, residual stresses in the products after that. So these provide good fatigue properties, this forging. So crankshaft, connecting rod, gears, blooms and slabs, coining, these all require good fatigue properties. So that's why you require forging. Okay, and extrusion will be for the uniform cross section. So like this, you can go through these and you should remember these. So I'll skip these, all these application part and move to effect of manufacturing processes on mechanical properties. Okay, so manufacturing processes affect the microstructure of metal during processing. So the microstructure in turn affects mechanical properties such as hardness, strength, ductility, toughness, fatigue and creep resistance, because your microstructure is decided by manufacturing process. Okay, so if you are choosing deforming processes, then you will be having residual stresses which will be providing good final mechanical properties. And if you are using casting and not any further secondary processing, then it will be giving you less hardness, less strength, less ductility. So therefore such variation in mechanical properties must be kept in mind for ensuring that and product has requisite properties for service desired. Next is cast structure. So for casting, you have low hardness, strength, toughness and ductility, and it has also probability of internal defects. So as I told earlier, in case of casting, you have gases entrapped in your material, and you can also have poor surface finish because of the sand molding, and there will be heterogeneity in microstructure as well. So there will be less isotropic properties, and these are various structures. And in case of welding, you can have different types of welding. Based on that, your properties will vary as well. Okay, so in case of liquid state, solid state and liquid solid state, you will be having different type of properties. In case of liquid solid state, It does not affect the base metal properties, but joint strength is poor. Okay, so braced and soldered joints, they are poor and they break easily, so we won't be using these joints in case where you require better tensile strength. Next is machining. So machining, so if you are removing some layer from your surface of your material, then you can either do it by mechanically, thermally or chemically. So all these will give you different type of last properties, final properties. So in case of mechanical, using shearing, you will be providing some compressive residual stresses. So it will be giving you improved fatigue and tensile properties. In case of thermal, you will be having a recast layer. So it will be giving you heat affected zone, which can change its properties based on metal system. In case of chemical, you won't be having any residual, okay, you won't be having residual stress. So lower fatigue and tensile properties will be there. In case of forming, so forming can be of two types, cold forming and hot forming. In case of cold forming, you will be having increased hardness and strength compared to hot forming, okay, because you are performing it at lower temperature, so your dislocations are not getting annihilated as it's occurring in case of hot forming. And it will be having reduced ductility and notches. It will be having reduced internal defects, because in case of forming such as rolling operations, you will be compressing your material mainly, so there will be less chances of any internal defects. It will be having better finishing and closer tolerance, and it will be having increased strength to weight ratio. In case of hot forming, you will be having controlled refined microstructure and improved mechanical properties. It will be having less anisotropic properties, and there won't be any residual stresses because of the temperature that you are providing. It is getting rid of any residual stresses. Now this is also important. You're most likely to get any question based on this in your exam, so you need to understand break even analysis. Okay, so in this case what mainly occurs, you have to select manufacturing process to make your product as per specification of required properties, so at the lowest possible cost. And since different processes offer different capabilities and cost per unit, therefore break even analysis is needed to select suitable process. And these are the various types of cost. So first is fixed cost, which is initial investment on equipment and tools, and it doesn't vary with volume or production. Next is variable cost, which varies with volume and production and includes materials, energy, labor, administrative overheads. Now this will keep on increasing with increasing units. So total cost formula will be fixed cost plus variable cost multiplied by number of units, and the total cost per units decreases with increase in quantity as fixed cost remains same. Now you can either directly put this formula for calculating your which method is cheapest, or you can plot this graphs as well. Okay, so from fixed cost, it will be a straight line parallel to your x-axis, and it will be having some value at 0 as well, and variable cost will be a line. Okay, now combining both of these, it will be giving you total cost. Okay, now when you will be purchasing, it will be starting from 0, because for 0 units you won't be requiring for 0 units you won't be requiring any money. Okay, so with increasing units you will be increasing your total cost in case of purchasing. Okay, so purchasing will always start from 0. And next is your when you are using some methods such as machining center or casting, then it will be starting at particular fixed cost. Now there are various now we have compared three processes: purchasing, milling and CNC. Now based on these three processes you can find various ranges in which these processes will be cheapest. So now you are given fixed cost and the variable cost. So variable cost for purchasing is 200, for B it is 75, for C it is 15, and fixed costs are 80,000 and 2 lakhs. Okay, now based on these equations you can easily find out what will be the break even, these points, these comparison points. Okay, so where these two equations will cross you can easily find out it will be 640 and next will be 2000. Now between 640 and 2000 lathe machine will be the cheapest, and below this your outsourcing will be cheapest. Outsourcing will be cheapest initially. Okay, you have to remember this part because it will always start from 0. Because if you are buying for example a box of apples, okay, a dozen of apples if you are purchasing, you won't be requiring any fixed cost. Okay, and if you are trying to grow apples on your own, then you will be requiring seeds and you will be requiring some land. So all these things you will be requiring, that will count in fixed cost. So any other option than the purchasing will always never start from 0. It will always start from a fixed cost. Okay, so next will be the one with the lower fixed cost, it is lathe. Okay, so it will be on second range between 640 to 2000, and above 2000 it will be your machining, which will be having higher fixed cost. Okay, it will be having low variable cost. That's why it is becoming lower in long range. Next is casting, introduction and suitability. This is the last chapter. So for casting, this is the definition. You should remember what is the casting. So casting is just a manufacturing process in which a liquid material is usually poured into a mold which contains a hollow cavity of the desired shape and then allowed to solidify. Okay, so next is suitability of casting. So these are the basically various advantages of choosing casting. So casting can be used to create complex internal and external part geometries. So compared to other processes, it can create very complex shapes as well. And some casting processes can produce parts to net shape. Net shape meaning final product don't require any machining. So there is no further manufacturing operations are required, and it can produce very large parts. So cast parts weighing over 100 tons have been made. It can be used with any metal that can be heated to its liquid phase. Okay, and for example polymers, metals, these can be easily heated to liquid phase and can be casted into various shapes. But ceramics are hard to cast because they have very high melting temperature. So they are used for powder metallurgy route. Some types of casting are suited to mass production. For example, sand casting, and these are castings which require very less initial cost. So they are suited for mass production. These are various examples of casted products which are casted for automobile. Okay, next up we went through some strengthening mechanisms. So these are the various mechanisms. So it is the ability of metal to plastically deform depends on ability of dislocation to move. Thus restricting or hindering dislocation motion makes a material harder and stronger. So some mechanisms that strengthen metals are as follows. So first is grain refining, second is solid solution strengthening, third is strain hardening, then precipitation strengthening, martensitic strengthening, and composite strengthening. So in case of grain refinement, you will be refining the grain size and you will be using this Hall page relation. You can use this relation to understand with increasing grain size your yield strength will be reducing. Okay, so it is an inverse relation between grain size and yield strength. Okay, and this relation will be only valid between some range, and if your grain size is very large or extremely fine, then this relation won't be followed. And why the grain refining occurs? So your grain boundaries, they are the areas where there are disturbance in the equilibrium spacing. Okay, so grain boundary acts as barrier to dislocation motion. So two grains are of different orientation, and a dislocation passing into grain B will have to change its orientation, and the atomic disorder within the grain boundary region will result in discontinuity of slip planes. Now for high angle grain boundaries, dislocation will not traverse across the grain boundary. In case of solid solution strengthening, your pure metals are almost always softer than their alloys, and adding another element that goes into interstitial or substitutional positions in a solution increases strength, and the impurity atom causes lattice strain which can anchor dislocations. Thus alloys are always stronger than pure metals. Now these are the impurity atoms, so these can be smaller or larger compared to your matrix atoms. Okay, so if it is smaller, then these impurity atoms will be exerting some tensile strain on the surrounding crystal, and if it is bigger, then impurity exerts compressive strain on the surrounding crystal. Okay, so this small impurity and large impurity is compared here, and the alloying with impurity atoms that go into the substitutional and interstitial locations, they improve strength and hardness. Okay, and high purity metals are usually softer and weaker than the alloys with the same base metal, and the alloys are stronger than pure metals because the impurity atom impose lattice strain on surrounding host atoms, and lattice strain field interactions between dislocations and impurity atoms inhibit dislocation motion. Next is strain hardening. It is work hardening, strain hardening, or deformation processes. So these all three are almost similar. So it is enhancement of strength with increased plastic deformation, and the strain hardening is the phenomena whereby a ductile metal becomes harder and stronger as it is plastically deformed, and it is also called work hardening or cold working because the temperature at which deformation takes place is lower than melting temperature, and the effect of strain hardening may be removed by annealing heat treatment, which is slow heating and slow cooling, and strength increases but ductility is sacrificed. Last is precipitation or edge hardening, in this technique it increases yield strength of malleable materials like aluminum, copper alloy, and stainless steel, and based on changes in solid solubility with temperature to produce fine particles of impurity phase which blocks the movement of dislocation in a crystal's lattice, and alloys must be kept at elevated temperatures for hours to allow precipitation to take place. This time delay is called aging. Okay, so that's it from my side. Now thank you for joining. Now I'll be closing the session. Okay, thank you.